What is Saturday's date this coming?
It's Pi Day.
It's March 14th. My favorite day. And so we're going to do some fun things in the Math Center. You are all invited. You should come and enjoy. We have a calculus event on Wednesday. If you haven't taken calculus, you don't have to do that, but it's fun watching. You know what a haiku is? On Friday, we'll do a paiku. Instead of 575, we'll do 314. Set yourself up for some poetry. There is a pi digit contest. If you recite the digits of pi, the fraudulent one who gets the biggest wins pi. Our winner last year recited 150 from memory. I only do 10, so I don't know. There's a trivia game as well, and that's this week. So come have fun. Meanwhile, you have stuff for me. So homework, please. Send forward. Okay. There are a couple of discrete distributions that we use most frequently. And they're based on what I consider to be two primary ideas. I want to start with the uniform distribution. Now, we are dealing, for the most part here, with distributions that are generating numerical data. So when I think of a uniform distribution, I think of something that generates a number. But our uniform distribution idea is based on our equally likely outcomes. And in my head, the perfect model for this is a die. Let's consider this example, and it doesn't have to be a regular die. It could be a funky die. But as long as all the outcomes are equally likely, it doesn't matter how many sides my die has. 6, 20, 37, doesn't matter. The idea is our uniform distribution with equality. Our variable, x, covers the values from A to B. So if I'm dealing with a die, that covers the values from 1 to 6. Or, as I said earlier, if it's a funky die, it covers the values from 1 to however many sides we've got. I'm just going to use a regular die to think about it. How many values are there between A and B, including A, including B?
Would it be like an infinite number of values? Like it just depends on
We-
the number.
We're looking at discrete options here. Think of this die. There are 6 options, right? If I think of going from A to B, range of ages, People's age is a whole number. College students between 17 and 40. Or traditional undergraduates between 17 and 23 most of the time. How many values are there? Well, if I think about a number line, and I'm only counting the number marks in there, how many marks are there?
There's like 5 marks there in
Oh,
between. Plus the dots.
But I need to keep everything, right? If I think of the die, there are 6 options, but it went from 1 to 6. If I do 6 minus 1, that's only 5 options. I have to remember to add back on. In general, this takes the difference between the two numbers and then adds on 1 to cover that extra, because if we subtract, then we're taking away this one at the end on the left here. So I have to put it back on. Now, equally likely means that the probability of any one of these events is the same. I have 6 options on my die. Chance of any one of them coming up is 1 out of 6. If I have B minus A plus 1 options, then the probability is 1 out of that many. Pulling numbers out of a bingo call, right? Pulling lottery numbers out of a bin. There are 70 numbers in here from 1 to 70. Chance is 1 over 70. Graphically, I can think of drawing a picture. And in this case, I would think about each X value in here having a height, and that height is 1 over B minus A plus 1. I think of this as a straight line. It turns out there, now I'm audio again. Let's try that again. I want to do the average. I take each number, I multiply it by the probability, I add them all up. If I do that, it turns out that what I end up with is the value of each one times the total. Since the probability is the same on each one, I can factor it out. I can just add up all the numbers from A to B, and I get this. There's a formula for that, adding up a sequence of numbers. We do this in a course called discrete math. The formula was basically developed about 300 years ago. But notice, these are going to cancel. Leo, what's that going to give me if these cancel?
It'd be A plus B over 2.
Which is
Then you can-
exactly the middle, the way you said it, wasn't it? That works out perfectly. If we think about the average is a balance point. Look at that picture. That little rectangle right there. That's a strip. If I'm going to balance that strip, I'm going to balance it right in the middle, aren't I? Halfway between A and B. My numbers go from 1 to 6 on a die. That means the average value of this die is 3.5. If I think about the options going from 1 to 6, A is 1, B is, that's 3.5. 3.5 is not an option on my die. What does that mean? Well, if it should be spread out equally, the median is not one of the values. That's acceptable, isn't it? Same idea here. So the average might not actually be one of the options I can use. In the same way, I can construct a formula for the standard deviation. Now, actually working out where this formula comes from, the major pain in the backside. I'm not going to do it. What I am going to do for you is tell you that you should go to page 202 in the textbook. And on page 202, there's a box. And this box has both the formulas for mean and standard deviation in it. What's more, it has a version of the CDF function. There's my PDF. The probability of any particular value is 1 over b minus a plus 1. That's exactly what we came up with. But what's this? It's the chance of being less than or equal to some particular value. Here's my picture. I want to go up to some point. I need to know this area divided by the whole thing. How many options are in this pile? Divided by how many options there are total. That's exactly what this fraction gives me. I like thinking of it as options like we were doing the counting formulas, right? So I'm going to use it that way. An example. I have a job applicant pool, and the ages of the people applying for the job are uniformly distributed between 20 and 60. So I look at my job applicants. Uniform distribution between 20 and 60 in age. Now, this is to the nearest year. So I'm not, you tell me your age, you don't tell me I'm 5.5. I did that when I was a little kid. I don't do it now. Leo, question?
Would the A and B be like A would be 20 and B would be 60?
Exactly. So that's my A and B. I would like you to compute for me the mean and the standard deviation. Fortunately, we have the formulas. Okay.
Route 40 for the the standard deviation are 11.54.
0.54. Hang on a second. Let me walk through the standard deviation calculation. I've got B minus A, 60 minus 20 is 40, plus 1, so this is 41 squared minus 1 over 12.
I'll get added to one.
Ah, that's actually really important, especially in a discrete calculation, right? Because if I don't add the 1, then I'm going from 40, but I'm not including 20, I'm only going to 21. So it makes a big difference in a discrete distribution. The reason I'm emphasizing the word discrete is because there are others that we'll talk about later in the week. Okay, so this is square root of 1681 minus 1 over 12. And now when you do that calculation, you get 11 point something else, right?
11.83.
Wonderful, 11.8. So now what I want to think about. So I want to think about doing probabilities with this distribution. So how would I calculate? What is the chance that when I pick an application at random, the person's age is more than or equal to 40? Now, I can just grab the formula out of the textbook, but I'm not going to. Hold on, Leo. I want to think about this in terms of options. How many options are there that are bigger than or equal to 40 in my sample space? Ages go from 20 to 60. How many of those are 40 or more? Almost. Right, I got to remember to add that 1 because it's 40 through 49, that's 10. 50 through 59, that's 10. And 60, that's the extra 1. So there are actually 21 options out of how many options were there total?
41.
Bingo. And now I have a decimal, which is a little bit bigger than a half. Now that's not the formula in the textbook. The formula in the textbook is for a CDF, which would give me from the low end up to and including 40. This is the reverse. I wanted 40 and above. So the other way I could think about this is I could think of take everything and take away all of those. See how I had to change the number, Jacob? Because I want 40 in the list, I need to throw out everything that's not 40 and lower. This is again where that adding 1 issue comes into play. I could also write this like this. Because if I'm strictly less than 40, then I'm less than or equal to 39. We are a discrete age setup. That I can use the CDF formula for out of the textbook. You get a formula sheet for the next exam. You get to write it. Gee, I wonder what should be on it. That was the hint dropping. What is the chance I randomly select an age, an application, and the age of that applicant is less than 30. Less than or equal to 30. Hold on, man. People are still chugging away at this. I can think of it 2 different ways. How many options are there?
It'd be two options, it could be like, my favorite lesson, instead it could be 11 out of 41, which gives you like.
Oh, hold that thought. That's exactly, there are 11 options. 30 and everything from 20 to 29, right? 20 to 29 is 10, and 30 makes 11. I can also do it by saying, hey, that's 30 minus 20 plus 1. There's the plus 1 again. Over, then I put, how many options are there total? 60 minus 20 plus 1. That's the formula for the CDF. X minus A plus 1 over B minus A plus 1. I don't have that formula memorized. I don't like memorizing formulas. I like thinking about my number of options. I think better in terms of the options sitting in front of me. But that's me. Questions? While this is a fairly direct computation, I don't tend to do an experiment a single time. I don't tend to just do one thing. I tend to do it more than once. So, what happens if I have an experiment I'm going to run, but I'm going to run it over and over and over again? I'm going to roll the die. Zach, give me a number between 1 and 6.
4.
Then a 4 is a success. Everything else is a failure. You roll anything other than a 4, you didn't win. You roll a 4, you win. What that's really giving me is two options, right? I succeed or I fail. A binomial distribution has two options. One is a success, one is a failure. Those designations are completely made up. But I tend to think of them that way because that's a clearer demarcation. Maybe it's more than just one option. Maybe rolling an even number is a win, rolling an odd number is a fail. However you want to do it. But I need a group of things that I win, group of things that I lose. These were created and explored deeply by a member of the Bernoulli family. I'm in trouble because there are 5 Bernoullis and I never tell which one did which. There's John, Johann, Jacob, Daniel, and another Jacob. I lose track of the Bernoullis fairly quickly. We refer to this repeated experiment as a Bernoulli trial. So I have this experiment I'm going to run. I'm going to do some number of trials. Let's say I'm going to roll 3 dice, or I'm going to roll 7, or I'm going to pick numbers out of the hat 15 times. However many times I'm going to do this. Let's code our options. Success is a 1, fail is a 0. If winning is rolling a 4, my chance of winning is 1 out of 6. What's my chance of failing?
It'd be a 5 out of 6.
Nice and easy, because they have to add up to 1. I don't know what my particular experiment. This case was 1 out of 6. But again, I could pick a funky die, and maybe the chance changes. One time I drop the damn thing, too many different places, right? There's a die with 8 sides. Doesn't matter. Maybe I'm doing something that is not related to dice at all. I'm looking at students and I'm looking at what's the chance I pick a student and they're in the School of Business. I can actually work out what that probability is. I hate the following notation. Remember I said that parameters usually get Greek letters? I want to talk about a proportion, a probability. They're going to use P. Oh, that's pi in Greek, and every time I see pi, I think 3.14, and that's not right in this case. That is a number between 0 and 1. This makes me crazy. Every textbook uses something different for this particular number. Some of them use the letter P. Some of them use the Greek letter rho, which is an R, but it looks like a P. I'm going to use the notation this book uses. So, the chance of success is pi. And that means that the chance of failure is 1 minus pi. I can think of this like test results, positive or negative. I can think of this like an inspection. It either passes or it fails. I can think of this in lots of different settings, but I'm going to do this experiment more than once. So what happens? Well, for one experiment, the average will be exactly pi. And it turns out that the variance is the product of pi times 1 minus pi. Again, I can calculate this explicitly. Calculation takes me about half a page. So I thought I'd just give you this piece of information. But I want to do this more than once. Let's let n represent the number of trials. And now what I want to ask about is not the probability distribution just of x, of succeeding or failing. I want the chance of getting a certain number of successes in this many trials. So my x now represents the number of times I succeed. My original example was rolling 3 dice. Zach told me that succeeding was getting a 4. So let's think about what could happen when I roll my 3 dice. How many 4s could I get?
3.
Because there are only 3 dice, right? But I could get none of them showing up 4. I could get one of them showing up 4, or I could get 2 of them showing up 4. So let's think about what could happen. I could have 0, 1, 2, or 3 fours. Those are my X values. What I want to figure out are the chances. Real, hold on. Instead of thinking about rolling 3 dice together, let's think about rolling 3 dice one at a time. So I roll my first die. Either it's a 4 or it isn't, right? Here's my second die. Does it care what happened over there? Which makes these independent events. Wait a second. Independent. We talked about this last week. What does it mean when events are independent with the probabilities?
Of like it doesn't change based on the instant.
Right, so that die had no effect on this die. So if I want to think about the probability of succeeding there, probability of succeeding here, it's the same. But also if I want to do both, right? So I'm counting it, did I succeed more than once? What would I do with those numbers? Since there's no influence, that's our conditional idea, right? And when they're not conditional, when they're independent, I can just multiply the probabilities together. So the chance of succeeding here gets multiplied by the chance of succeeding there. Here comes my third die. It doesn't care what either of those did, right? So I multiply again. There's a lot of multiplying going on here, isn't there? But because they're independent, it's just direct multiplying. Let's pick one of these options. I have a die with both sides. It says I should use 2. So we're going to use 2. What is the chance that 2 of these dice came up with a 4? The chance the first die came up with a 4 is 1 out of 6. The chance the second die came up with a 4 is 1 out of 6. But the third die should not be a 4. What's the chance of that happening? 5 out of 6. So 1 out of 6, 1 out of 6, 5 out of 6. However, that put them in a particular order, didn't it? Uh-oh. Say anything about order up there? So it could be not that the last die was not a 4, but maybe the second die wasn't a 4, and the third one was. Or maybe the first one wasn't, and the second one and third one were. So I have to worry about the orders, right? Hang on a second. We counted those, didn't we? We counted the number of ways to line stuff up and to pick stuff. I need to know which ordering things happened in. I want 2 out of 3 to be 4s. How many ways can I select 2 dice out of 3 dice? That's counting for me. That was Wednesday, week before last, before break. It's counting for me. I've got 3 items. I want 2 of them. And I don't care about the order. Say again? Say again?
3.
It is 3, but how do I get that formula? What's the formula for getting that 3? It is 3. Because I can pick these 2, or these 2, or these 2. How do I get that formula? A very important word is in the sentence I have just written on the board. I need to know how many ways I can choose the 2 dice that are going to show a 4.
It's like, it can happen however many type of ways, so you multiply. The one, like N1 times like N2, and then N3, because all the different types of ways. Something like that.
That's our multiplication formula. That gives me the total number of options, right? But now I'm thinking of just the options that will return 2 coming up. We did this with coin flips, right? We built a tree diagram with heads and tails. I'm thinking the same idea here. But I only care which of the options I get. I want you to reach into my hand and pull out 2 dice. If I tell you to do that, does it matter what order you selected them in? That's where our object changes. Because now we're talking about ordered selection and unordered selection. There was a formula for those. Somebody tell me what was the formula that dealt with unordered selection? Chris?
The and choose R.
Right. In our case, it's 3C2. Out of our 3 dice, we are choosing C, 2 of them. And since I don't care about the order, I'm just reaching in and scooping up my 2 dice. There's the C in my hand. The formula for that is 3 factorial over 3 minus 2 factorial, 2 factorial. Or there was a button on the calculator that had an NCR on it. Should go back and look at Wednesday's lecture from the week before break. Which, you are right, Chris, turns out to be equal to 3. That's the number I get when I do this. Now, here's the fun part. Independent probabilities get to multiply. I wanted 2 of them to come up 4. So I think about the chance of succeeding, right? It's going to happen twice. So I'm going to multiply that twice. Shorthand for multiplication of the same number is a power. 1/6 times 1/6, 1/6 squared. And then I need 1 of them to fail, right? So I need 1 of them to fail. Hey, wait a minute. This takes care of the ordering. This takes care of the 2 successes, and this takes care of the 1 failure, regardless of the order they occur in. That's what that number out front tells them. It takes care of all the possible orderings. By the way, this works out to 15 over 260. I have no idea what the decimal for that is, but you're welcome to calculate. It doesn't matter at the moment. What I will tell you is that this idea works no matter how many trials we are doing, no matter what the chance of success is, no matter what the chance of failing is. In general, Let's use the same number, same variable. I will have n trials. I want x successes, little x, some number. And pi is the chance of one success or failure on one trial. Then the chance is n choose x times the chance of success time raised to the number of successes I want. And then multiply by the chance of failing raised to the power of the number of failures I want. X is a whole number value between 0 and n. It is possible that I will roll these 3 dice and none of them will show a 4. It is possible I will roll these 3 dice and all of them will show a 4. But there's no way I can roll 3 dice and get 5 of them to show a 4. And here's the better part. This is called a binomial distribution. This is the PDF formula right here. That's the formula for the PDF. So if I tell you, oh, I'm going to do 12 trials, how many times do you want to succeed?
You may say 6.
Okay. Now I need to know what the chance of success for any one trial is. I'm going to pull this out of thin air, and I'm going to say that there is an 80% chance of success. This is a good thing. It's easy for us to do, right? I now know exactly the chance of getting 6 successes out of 12 trials. Just going to plug in these numbers to this formula right here. I've got 12 choose 6 times 0.8 to the 6th times 1 minus 0.8 to the 12 minus 6. The power on the first set of parentheses is the times I want to succeed. Chance of success, number of successes. And then chance of failure, number of failures. Now, I'm going to do one more thing by hand. I'm going to simplify the 1 minus 0.8 and the 12 minus 6 in the last set of parentheses. Then this goes right here. 12, hit the math button. Probability is in this pile. There's my NCR. 6. That's the first number. There are 924 different orders for me to succeed or fail. Then I need to take that number, multiply by 0.8 raised to the 6th, and multiply by 0.2 raised to the 6th. There's my chance. The chance of getting exactly 6 successes is pretty small, 1.5%. $1.55. I can go you one better. This is a distribution. I'm going to use the same formula over and over and over and over again, right? Above this key, what does it say?
Distribution.
So if I hit second variables button, there are distributions there. See the little arrow pointed down? Let's go down. Ah, binomial. I hit enter. How many trials am I doing? I was doing 12 trials. Chance, right? The P is the chance. 0.8 was my chance of success, and I wanted 6 successes. It did the work for me. The same command exists in Excel. Equals binom.dist, the binomial distribution. I'll make it even nicer. This is just a formula, right? Let's generate a spreadsheet. Here's the appendix in the back of your textbook. Please notice what I've got here. I've got an N, an X, and then a whole bunch of different options for our probability of success. I was doing 12 trials, right? 12. That means N should be 12. 3, 4, 5, 6, 7, 8, 9. I turn the page. There's 12 trials right there. Please notice, for some stupid reason, the textbook skips 11. I don't know why they did that. I had the chance of success was 80%, yes? There's 80%. That's the column I want. 12 successes. Sorry, 12 trials. The next column is the number of successes. 6 successes, 0, 1, 5, 5, the exact same number. Do I actually have to do the math? Nope. I love this table. I use it all the time, but that means I can answer other questions with it, right? We wanted to know the chance of getting exactly 6. What's the chance of getting 4 or fewer? What's the chance of getting 4 or 3 or 2 or 1 or none? So that's the chance of 4 or 3 or 2 or 1 or 0. Notice these dashes? That means the chance is less than 1/100th of 1%. That's effectively a 0 as far as this book is concerned. You want another chance of getting more than 9? 10 plus 11 plus 12. There we go. I just add up these numbers. Having discrete options and this table allows me to do a lot more. On our Canvas page, in the data files from the textbook section, there's an expanded version of these tables. The expanded version includes both the PDF and the CDF, if you want to download that to have it. This will be provided to you at the exam. Okay, there are other types of discrete distributions that we won't cover. These two are the most common in business settings. I'd be glad to talk to you about some of the others. I will start looking at other distributions on Wednesday, not discrete ones, but continued ones. Yes,
Do you invite the?
it's already up.
Okay.
I will see you all on Wednesday. Have a wonderful rest of your day. Thank you. Yes.
When's our test again for the next test?
2 weeks from Wednesday? I think. Might be 2 weeks from Friday. Gotta double check.
We have a game Saturdays, away, so we're gonna leave Friday
Yeah,
morning.
So I need
We'll
to
send you-
send me the form, but then we need to work out when you're gonna take it before you leave.
Yes,
Ideally Thursday, if you guys are leaving.
well, you said next Friday,
But yeah, it's 2
we're
weeks.
leaving this Friday.
Oh, no.
Yeah.
So she'll be just the.
Yeah, we'll send you.
Yeah, no problem. Thank you.
Thank you,
Make sure everybody's name is on it.
thank you.
Thank you.